Yes, so the title of my talk is Focusing Gentzen's LK Proof System. So I assume most people know about sequent calculus, so I'll go over the basics. And this is based on a paper, sorry, that Chuck Liang and I have written, and it's on my website. Also, if you go to the website, you'll also find the slides I'm using right now. So what's a good foundations for computational logic? So I'm thinking, like, if we were to try to find a way to teach, to write a good textbook, to give a good foundations for many topics in computational logic, improving over what we sort of see now in the field, what would be a good foundation? So part of my answer would be, I think proof theory goes a long way, but we have to improve on what Gentzen originally proposed to us. And by computational logic, I mean sort of all these topics at least, if not more. So I really have a broad spectrum of things that I'd like to talk about. In this particular talk, however, I won't focus on all those things, not like induction, for example, but I'll just talk about Gentzen's LK system and improvements to it so that I could use that to teach part of, say, computational logic in a meaningful way. And again, this is for me as a computer scientist. How could I improve Gentzen? So here's Gentzen's rules. It's two-sided. It's very close to what he wrote himself. I'll make a few comments on the next slide. It's two-sided. I have explicit contraction and weakening on left and right. I have these sort of multiplicative versions of initial and cut elimination, and then the introduction rules are there for connectives. One difference, I have the units false and true. Oops. Yeah, false and true. Gentzen didn't use those. Also, he had a negation, and here for negation, I mean implies false. So let's make a few observations about what I just presented. So the structural rule of exchange is built into this presentation. So the left and right are probably multi-sets when we get careful. The additive variant of the conjunction and disjunction rules are the ones given, not their multiplicative variants. Implication is given, although classically it's not strictly necessary, because implication can be thought of as a disjunction, but in that case it would be a multiplicative disjunction. And Gentzen used negation, as I mentioned, but we'll use implies false. As a result of making this one change about negation being implies false, you can take the usual restriction on LJ, which is this one single conclusion versus multiple conclusion restriction. The way Gentzen wrote it, he said the right-hand side has 0 or 1 formula in it. Here, when we make this change in negation, we can actually say there exists exactly one formula on the right, always. Or another way I'd rather say is the right-hand side is linear, right context is linear, and the left is classical. So in this way, intuitionistic logic can be seen as a hybridization, let's say, of linear and classical logic. However, I won't speak much about intuitionistic for the rest of this talk. Now, I'm going to take 4 shots at the sequent calculus and tell you what things I don't like, especially, say, coming from computer science and the way we use proofs, would like to use proofs in computational logic. And there are these 4 items, and I won't go through them right now because each of the next few slides goes into detail. So I'll repeat them as I go along, but there's 4 of them. So one is this collision of cut and structure rules. So this is fairly well known, so I'll step through it quickly. So there's an instance of the cut rule where C is the cut formula. In the event that the right premise of the cut has a contraction on the C, this cut can be eliminated. You do so by the diagram below. You double up the cut, okay, and you put lots of contractions in, but it's kind of clear how to do the cut elimination step there. If you had a contraction on the left branch, then you can still remove the cut in a very clear way. You again get 2 cuts when you replace this one cut, and you stick in lots of contractions as well. This time also on the right. Okay, so however, in the classical setting, the full classical setting, you can actually get contraction appear on the left and the right together, in which case there's nothing but non-determinism going on here. This is a rather messy situation, if you will. You can eliminate the cut, of course, but there's nothing like an algorithm or a clean cut algorithm going on here. Now, in the intuitionistic setting, this non-determinism is avoided because you just say right up front, there is no contraction on the right. So this can't happen, and because basically the previous example can't happen. Okay. All right. So that's one problem with cut and structure rules in Gentzens calculus. These things occur, and it's sort of, if you're thinking of the Curry-Howard isomorphism in classical logic, and even sometimes in intuitionistic logic, you want to avoid these kinds of non-deterministic choices. It's like you've given yourself too many proofs, too many programs to compute with. And this even gets worse if you have weakening. So this is a standard example where you prove B two different ways. Sorry, you prove B two different ways, then you weaken, and then you do a cut, a contraction. Okay, and now when you want to eliminate the cut here, this proof could be either psi1 or psi2, and it's you know, they don't share any relationship with each other. So this is really highly non-deterministic. These are often called Laffont's counterexamples. That's what I'll use that term, and I'll return to it in a little bit. And they're ruled out in intuitionistic logic, but not in classical. But we can say something a bit more when we get to focusing proof systems. We'll see they're also ruled out, but maybe for a deeper reason. So that's one problem. The second problem is also quite obvious. If you have a proof, sequent calculus proof, then it's all these permutations exist. The two proof fragments I show, they're technically different, but in fact, there's nothing interesting about the difference. And one might argue they shouldn't be different. And it's the existence of such permutations, which is probably the main reason for the revolt against sequent calculus that you see. It gives rise to things like natural deduction instead of sequent calculus, or expansion trees or proof nets, some more parallel notation for proofs. So that's a second serious problem with the Gentzen sequent calculus. Not such a serious problem, but still an interesting one, is the typical way to present sequent systems is to say and is either added, you give the additive or multiplicative version, but you have to make a choice. So Gentzen, for example, gave the additive versions in his system, but people in theorem proving usually like to have invertible rules as much as they can, in which case the disjunctive, the disjunction would be the multiplicative version in order to get invertibility. You do this because you can arrange essentially everything to be invertible except for the existential right rule. Now, why? So a good question is, why not just allow both additive and multiplicative versions? If you take one and you have contraction and weakening, you can get the immiscibility of the other, but still it seems a big step, I mean, a natural step. Why not just have both? So we'll see a proof system which has both in a moment. And the fourth problem is there's no provision for synthetic inference rules, big step rules. So for example, here's a formula displayed. It says, it's an axiom, you might say, that says path, whatever binary predicate that is, it's transitive. We're allowed to assume it's transitive. Now, if I were to use that formula in a proof in, say, Gentzen's system, I would have to have at least 5 introduction rules just to make use of this one rule. But of course, it's much more natural to think of using that axiom in this form. In other words, to prove path xy, you prove path xy. No, sorry. In order to prove, reading back up from conclusion to premise, xz, try to find a y such that you can go from x to y and y to z. Okay, so that's the usual, let's say, back chaining interpretation. But there is another equally valid use of this. If I have 2 assumptions of this form, x goes to y, y goes to z, then I can add another assumption that says x goes to z. All right.
Dale,
yes.
Do you have the Zoom chat up? I noticed there's a comment from Anupam and Sonia in the chat.
I see it, yes. You might have to remind me though. Presumably for invertibility, you want multiplicative on the right and additive. Yes, sure. Well, wait, Chuck is, my co-author is chiming in. Yeah, you don't want to confuse additive and multiplicative. You know, the left rule should, if you're choosing additive, you'd want the left rule and right rule to both be additive, and similarly for multiplicative. So when I say we add it, I don't mean we're going to add two conjunctions. One is the additive conjunction, one is the multiplicative conjunction. So you need to keep them separate, or otherwise you lose sort of elegant parts of the cut elimination theorem. Yes, okay, I'll watch the chat. Okay, so what you really want, especially in the application of sequent calculus to computational logic, you really want these much more big step rules if you can, right? In fact, the two rules I highlight in the middle are logic connective free, right? They're just about atomic formulas. And in many ways, it's quite nice. If you have a rich proof system sitting around with context and turnstiles and left and right, that's already a bit of logic that you can, you don't want to repeat with an implication and universal quantifier if you can help it. So we really want to have these larger scale rules. So, but the real question there is, how can we build them, and how can we guarantee that when you add them, you keep cut elimination in your proof systems? Okay, so all four of those topics I'll come back to after I show you what I would claim would be the improved version of LK, or at least a new version of it which addresses these issues. So in order to do this, we're going to introduce LKF, for F for focused. And this proof system doesn't deal with formulas so much as polarized formulas. Okay, so all the connectives you see here in the first line will have the propositional connectives will have a plus or a minus attached to them. So I have a plus on one and a negative also on an and. Okay, so I have positive connectives including existential and negative connectives including universal. I also have to classify literals as being positive or negative also. So first of all, literals are atoms or negated atoms. So the only use of negation as a symbol will be in front of atomic formulas. Then I also have to have a notion of bias assignment for atoms. So it's just some function that maps atomic formulas to plus or minus. So it's just a piece of data that says this atomic formula is plus, this other one might be minus. And then we extend it to literals just by flipping the polarity sign whenever there is a negative, whenever there's a negation in the literal, okay? Then finally, we say a formula, a polarized formula is positive if its top level connective is positive, or it's a positive literal. So we only look at the top level structure. We don't look inside to make this determination. It's positive just on the surface. It's negative, and similarly, just on the surface. And for this talk, I'm going to require that this bias assignment, delta here at the bottom, is stable under first order substitution. In other words, theta of an atom is equal to theta of any substitution instance of that atom, which is essentially to say that the polarity of that atom is determined by its predicate symbol. Those two are equivalent statements. Okay, so that's polarized formulas. In Gentzen's original system, we'll talk of those as if they were unpolarized. Linear logic has different names for these symbols, so I just want to show you there. And in case you weren't clear about what's multiplicative and additive, I have the multiplicative connectives are listed here with their linear logic names. I prefer to say or negative for par and or plus for O plus. And so I will, for the rest of the talk, I won't show linear logic connectives per se, just the ones with the plus and minus instead. And just to point out that logical connectives actually have four attributes: arity, whether or not they're additive, multiplicative, what's their polarity, and conjunction, disjunction. If you fix arity, and you know two of the others, you can determine the third from those two. And notice that De Morgan duality flips the last of these two. In other words, it makes a conjunction into a disjunction and vice versa, and changes the polarity by flipping it, but does not affect the arity. Obviously, the arity means a zero arity would be the unit, for example, and binary would be the usual way we write the connective. That's not changed either. And you don't change multiplicative or additive nature of the connectives. Okay. And finally, all formulas in LKF are actually in negation normal form. That just means there's no implication. They're not part of the polarized syntax at all. And if I want to, and negation has only atomic scope. Well, in fact, I'll lift negation now to arbitrary formulas, but in that case, I think of it as a function. So a function implied a negation of a negated atom is the atom underneath. And if I negate the other connectives, they just do the usual De Morgan flip of things, okay? And notice every time I do a negation of a positive, I get a negative and vice versa. Okay, and then we have a notion of polarization, which is this last line here. If I have an unpolarized formula, then a polarized version of it is anything I get by placing pluses and minuses on the logical connectives there, the propositional connectives. Okay, so if I have n occurrences of propositional connectives, I have 2 to the n ways of making it polarized for that. And I also have to determine the bias assignment for atomic formulas or predicates. Okay, so if I have m predicates, then I have 2 to the m ways that they could be polarized as well. So this piece of information here, this pair at the bottom here, would be a polarization of P, if you will. All right. So now, sequence in this system are, well, I'm going to make them all one-sided, so the proof system is a bit smaller and more natural in some ways. And I'm going to have an up arrow separating two collections of formulas, and a down arrow separating one formula and a collection of formulas. The gamma will be a multi-set of formulas, and theta is in here as a set. It could have also been a multi-set, but for technical reasons, we're using sets here. And A is a single formula. And I'll sometimes refer to the formula here, theta, as storage. And that's partly because all the action in the proof system occurs between the turnstile and the arrow, on either up or down arrow. So the storage is dormant. It's only used once or twice in a proof system in a very specific way. All the other time, the action is between the turnstile and the arrow. Okay, so here's the entire LKF proof system. So I have introduction rules for negative connectives here and for positive connectives here. Notice that this setup here, these negative connectives, have only up arrows in all of those. So if you're proving something from the bottom and you just did a negative introduction rule, then you must stay negative up arrow there. And every one of these inference rules would be classified as invertible in, let's say, typical Gentzen style setting. And here, the positive rules, say they have down arrows, okay? And so here, you find here the typical non-invertible rules. So the existential rule and the O plus rule. This is the non-invertible OR. The invertible OR is up here, this one, okay? Now, but as it is right now, these two different phases, if you will, involve different arrows that don't talk to each other. So they're glued together by the following. If I'm in by these other rules, and I'll describe them each, if I have P as a positive literal, then, and a positive in the sense of bias assignment, and I'm in a down arrow, then the proof ends if I can find its complement in storage, okay, if it's been stored. And if it's a negative atom here, I don't use this rule, even if its complement is stored. Okay, you just don't do it. If it's a positive literal here, you check the storage. What does it mean to store something? If Q, as I say below, is either I'm in the up arrow phase, trying to take care of invertible formulas, and I get to a positive formula. That's typically a non-invertible rule. So I say, I'm in the invertible phase, taking care of all the easy stuff. So I'm just going to store it, and I'll come back to it later. So Q moves from the left context to storage. If I'm in the positive phase, trying to take care of, let's say, non-deterministic or backtrackable things, and I get to a point where, oh, this is invertible. This is a negative formula. This can be treated invertibly. Then you just release that activity and you go into the up arrow phase, and then you do the invertible rules only, okay? And finally, if there's no formulas, you have an up arrow here, and there's no formulas in this to the left of the up arrow, then I have a special kind of sequent, and it's called a border sequent. I'll mention that in a moment. And at that point, you take something from storage and you put it into the focus. So the down arrow, the formula in the down arrow is often referred to as the focus of the positive introduction rules. Okay. So hopefully that high-level description is clear if you haven't seen it before. A few observations to make. I list them on the next slide, but I can draw them out here. Notice the only time you have contraction in this proof system is with the decide rule. So you only do contraction on a positive formula. If you have very few positive formulas in your proof search, that's great in some sense, because you'll have almost no contractions and the proof looks very linear. What else to say? And the only time you ever do weakening is in the initial rule, or in the T plus rule. I would say that's also weakening. So you're only weakening positive formulas or possibly negative literals. So notice that if you're a negative formula and it's a logical connective at the top level, then you never contract and you never weaken. You will do an introduction rule for it. It's really the sort of the linear core of the calculus if it's a negative connective. So for example,
Dale, a question. We're to understand that theta here is a set, right? In this presentation.
Theta is a set, yes.
So in the store rule, imagine reading bottom up, theta, if it already contains Q, then when you move the Q over to the right-hand side of the up arrow, presumably the two instants get collapsed into one.
Yeah, presumably, yes. So in fact,
you have a sort of weakening there.
It's a sort of contraction.
Well, oh yeah, okay.
Yeah, so I'm happy to call that a contraction. Yeah, that's why it's not a multi-set, it's a set, because implicitly there's a contraction here. So for example, the additive rules copy the theta to both sides, and the down arrow rule here copies the theta to both sides too. So there's an implicit contraction there. Okay, yeah, all right, that's a good point, Chris. If I remove these implicit contractions, you'd actually get back to mul, a focused version of multiplicative additive linear logic. All right. Yeah, so that's right. So we bake into the storage contraction and weakening in this proof system. All right. So however, okay, so if you're a positive formula, you can be weakened and contracted. If you're negative formula, if you're negative literal, in a certain sense, you can also, but they're usually only on the edges that this happens. And if you're a negative formula, which is not literal, then it's absolutely a linear maintenance of that formulas, that subformula. Yeah, any other questions quickly? I'll make those observations here. Well, first of all, we say that a polarized formula has an LKF proof. If this is your initial starting, you put it between the turnstile and the arrow with an empty storage. So that's the root of an LKF proof, if you will. Storage is non-decreasing as we move from conclusion to premise. And the key observations I mentioned, contraction only occurs in the decide rule, and a negative formula is never contracted, except if it's in storage, if you will. And weakening occurs only at the leaves. And it's only for positive formulas and negative literals. So that'll be an important thing, the observation we'll say in a minute. And finally, here's the completeness theorem. If I have an unpolarized formula, which is a theorem of LK, and I have a polarization of it, now remember there's these exponential number of them, then every one of those exponential polarizations has an LKF proof. Okay, so polarization has nothing to do with provability, but it has a lot to do with the structure of proof. And so we'll see some examples of that. So in many ways, polarization is all about controlling the size and structure of proof, which is quite relevant for things like cut elimination or proof search. This result was first proved in a paper with Chuck in 2009. We did it in a rather complicated way using intuitionistic and linear logic to prove this classical logic result. We have a more recent paper now on our web pages where we do it directly. It's a much more interesting proof, I think. And what's the structure of, say, cut-free focus proofs in particular? So here's a sequence. We'll call these border sequence. In other words, the only formulas are those that have been stored. Everything else has been processed, if you will. And so this is an important sequence just to kind of to denote, because in fact, we're going to call synthetic inference rules essentially those of the following structure, and I have it drawn out here. At the root, I have a border sequence, and then I go through different phases. And then at the top, all I have left are border sequence, if anything is left. Okay, so I go from border to border. In between, I must, to prove a border sequence, I have to do a decide. So I pick some formula in there to decide on. Then I do a bunch of down arrow rules, which may cause a conjunctive fan out. And then at some point, I have a down arrow possibly on a negative formula, at which point I release and I enter the up arrow phase. Then I do invertible rules to exhaustion, and that would leave this one zone presumably empty again. And then I could restart this phase. But in the process, storage has now probably gotten bigger, right? That would be the goal there. And so it's the synthetic inference rule is this border to borders, in which case I would just drop the up arrow in each case and say that's the big step rule that these two phases highlight. And we know certain other things, that if this formula P is say a geometric formula, for example, a horn clause, then the synthetic inference rules only involve atomic formulas. We can make these kinds of restrictions. Okay, the cut rule for LKF. So there it is at the top. Okay, so it's only involved in the up arrows. So if you have storage and nothing else, then at that moment, let's say we allow cuts. So it's really at the moment of synthetic rules, at the borders of synthetic rules, we're allowed to do a cut. We get this sort of thing. So we introduce B in one place and not B in the other. And notice one of these will be positive and one of these will be negative. So one of these will be an immediate storage, but the other one will be an immediate introduction phase for that formula B. In the process of proving cut elimination, we actually have to introduce 4 kinds of cuts. One of these generalizes the one above. And so, and that's not too surprising, because even when you talk about proving Gentzen systems, you have a notion of the key cut and the cuts on the side. And so we have all this vocabulary here. That vocabulary is actually denoted strictly by certain kinds of up arrows and down arrows occurring. So it's just the same thing in many ways. Now, how do I prove the completeness of, what's the outline of the completeness proof for LKF? That's the main result here, let's say. So this is one way to prove it, and this is what we've done in our most recent paper. We show that all 4 cuts I mentioned earlier are admissible. So the simultaneous induction on permutations, it's a more or less standard kind of structure. Although we do have an interesting control on contraction, so it appears a bit differently than typical, but it's not so different. And it's first order, so the proof is just by a straightforward induction. Then we have to prove the admissibility of the general notion of the init rule. So notice every init rule, initial rule we've seen in the focus system, is for atomic or literals only, okay? But it holds for general formulas. And it's actually not so easy to prove that it holds for general formulas. But okay, so we have to prove this as well. Then we have to prove some invertibility lemmas. And then what you can do is you pick a polarization. There's a way of taking Gentzen's LK system, which is on unpolarized formulas, and map them into polarized formulas. And once you do that, you can then prove that all LK rules are admissible in the proof system LKF. And that completes the completeness theorem. So basically, we're doing cut elimination on focus proof systems, and then trying to show that that can be emulate sort of arbitrary inference rules. And then that's how we embed LK into that system. Okay, so I won't do any more details except just to outline this notion of proof, how the proof goes. Now, what I will do for most of the rest of the talk is talk about applications of LKF. So I spoke that I wanted to have an improvement on Gentzen systems. So I claim this as an improvement. So let's see what I can do with it. So one immediate thing is I can prove that LK, the cut elimination theorem for LK, it follows immediately from LKF. Notice I didn't assume anything about LK. I showed you a picture of LK. I said, it's not really the system I want. So we moved the focusing. We did all the cut elimination, everything there. And now if you really want to know that cut is admissible in the first proof system, it falls out immediately now from this cut elimination theorem. Not surprising, but it's there. All occurrences of L'Enfant's examples disappear, and you can see why. Because in the cut rule, exactly one formula is positive, one formula is negative, or one of these cut formulas is positive and the other is negative. And as we've noted, only one of those is subjectable to a contraction and weakening, the positive ones, okay? And as a result, the typical examples disappear. I mean, the negative literals could also be involved, but they're always at the edge case, and there are initial rules right with them. So the main observation is polarization fixes this problem with L'Enfant. So in other words, you're throwing away a lot of proofs, and I'm not sad to see those go, if you will. Another application, we get synthetic rules now for free. So let's just work through an example. So I showed you the path, transitivity of path before. If I wrote this as not an assumption, but a formula on the right sequence, I'd have to negate it like this. I would polarize it this way with a positive and in both cases. So that was the only, I could put a negative and or a positive and, but if I put the positive and, we get nice things, which we'll see here in a minute. So let's say theta, I'm going to build this proof here at the bottom. Theta has this formula in it. If I now decide on it, instantiate it with some values, 3 quantifier instances, and then I split the conjunctions, I get this rule. So I have to prove 3 things. Okay, I have 3 subproofs, but now I don't know how to proceed because I didn't say what the polarity of path is yet. Okay. Now, so we have 2 choices. Path is all path atoms are positive or they're all negative. So if they're all, say, if this is positive, path is positive, then we know this has to be initial. There's no choice. This has to be, psi1 has to be initial, psi1. And its complement must be, the negation of it must be in theta, already in storage. Similar, the same observation for psi2. And the opposite is true here, psi3. I don't even look in theta at this point. I just say, okay, that's a negative formula. I'm in the down arrow. I must do a release. Okay, so let's take a look at what that means on the next slide. So that means, I just described, if the atoms are positive, I've just described this one in the middle here, that I actually described this rule, right? That those negative paths must be present. And then when sorry, let's go back previous slide. So again, their negations must be here. So even at the beginning, for this phase to work as far as it is, the negated path RS and the negated path ST must be in the bottom. And then I must release and then store this atom. So I add it to the context. So I get this rule here in the middle. So I've just described what is usually called forward chaining in the logic programming literature. If all the atoms are negative, let's go back, then this is positive. So its complement must have been in RT, path RT must already be present at the very root. And this is negative, hence I do a release and store and a release and store. So I get this rule. I get a branch here where that's been stored, and I get a branch here where that's been stored. And this is usually called backchaining in the literature. These observations were known back in 2008 by Kostov and Frank Fenning and his colleague, their colleague. They have a nice paper there. In a more recent paper with Sonia Maran, Elaine Pimentel, and everyone here is online. Thank you. And Marco Volpe. We have a more recent paper where we show more generally how this can be done, and that when you add synthetic rules that you build in this way to a proof system, you keep cut elimination theorem. So we get that for free from the focusing meta theory. Another applications of LKF, you can immediately get Herbrand's theorem. So what's that and how? So let's assume we have a formula with a quantifier prefix, some sequence of existentials, and then B is a propositional formula. So Herbrand's theorem says this is a theorem if and only if there's a non-empty set of first order substitutions for the variables x1 of the x bar variables, such that this disjunction of all those instances is provable. Now, this is easy to prove because of using LKF. What we do is we say, because this is, we're going to prove it in the one direction. So it's because it's provable, it has to be provable in LKF for every polarization. So we can pick whatever we want. So we pick a polarization in which the propositional connectives are all negative. So they're invertible. There's sort of no information content, if you will, to be given to them. Now, since the existential is provable, completeness says both this first sequence and hence the second one, focus sequence, are provable. It's just, their difference is just the storage. They must have LKF proofs. So then you take that LKF proof, and every time you do a decide on that stored formula, this existential, every time you do a decide on it, you'll get a sequence of existentials immediately, right back to back to back to back. Existential one, exists x1, exists x2, exists x3, because it's a down arrow. That down arrow must persist through all the existential instantiations. So whenever you do a decide, you can read off an immediate and complete substitution for that's just been chosen in that existential block. So now you collect together all the substitutions that you've seen in this particular LKF proof. And then you write down a formula C, which is just collect together those instances. And then then you just take the original proof, focus proof, and then you edit it. Every time you see an existential B hat formula, replace it with C. And in the phase where you make an instance and essentially choosing theta I in that particular instance, the corresponding one would you also pick the theta I, the B theta I disjunct as well. And so these proofs, you just edit that one phase with another phase. One goes through a sequence of existentials, another goes through a sequence of ors, and you're done. The rest of the proof structure, where all the propositional connectors are addressed, are identical between the two. And now we're finished with Herbrand's theorem. Pretty straightforward. Okay. Another final application, we can also host and describe other proof systems. So some of you may be familiar with, sorry, in order to do that, I have to introduce what are called delays. Delays are kind of trivial thing. I want to possibly take a large block of connectives, say that are all positive, and break it up for certain reasons. I want to put a negative in the middle, if you will. And so it's very easy to do that. You can define these delay minus of B to be, just take the B formula and say negative false or negative B. Okay, so this is clearly a negative formula no matter what B is. If it's negative or positive, this is going to be negative, and it's going to be logically equivalent to B. And you could have done it with a conjunction and its unit, or a vacuous universal, or you could, and you can do the positive delay in the dual sense. Or sort of maybe a more honest thing to do is just to say, we already had a zero array version of, say, a conjunction, and a binary version. Why don't we just have a one array version? So if we're allowing ourselves one array versions of connectives, then these are the delays, strictly speaking. And usually when we talk about polarizing formulas, we not only allow you to sprinkle in pluses and minuses and determine the predicates, but we'd also allow you to put in delays if you wish. The theorem stays the same about completeness. So if you have that, then you can mimic lots of other proof systems. So for example, LKQ and LKT, these are rather old proof systems by now. And just for the sake of completeness, I mean, we can write this in that fashion. We can take their formulas, write it in classical logic using this polarization and the assumption that all atoms are negative. And then what the cut-free proofs produced in LKF of that image is exactly the proofs of LKT. And if you choose atoms to be positive and you do the things slightly different, you put a delay or two in a different place and use positive and negative connected slightly differently, then you get their LKQ calculus. Now you could, I don't know, you could remove some of these delays or insert more, and you get either more aggressive focused or less focused proof systems. It just happens to be that the way they wrote LKF, LKT and LKQ, they had this kind of focusing there. And if you really want to get back Gentzens LK system, you can do that as well inside LKF. You just polarize in such a way that after every logical connective, you put a delay on both arguments. Okay. So as soon as you do one, if you do the OR, Gentzen had it as the additive one, which is O plus. So as soon as you do the OR, you put a negative delay on the arguments. Okay, so that would stop a phase of LKF to be just one connective deep. Okay, so we can host all those other systems. There's one more variant of focusing worth mentioning, and that is multifocusing. So that would be a setting where you would allow between the down arrow and the turnstile possibly many formulas. So you're focusing multiply. And the rules would be these, modified. All the other rules would be the same, except for the 5 I show here. So I have to change these rules, of course, to work on, say, some formula in that context. The release rule has a proviso that I can release only when everything in this delta is negative. So that would be one formula release rule. And the decide rule would essentially say you can take any number of formulas from the storage, and this, as long as they're positive, as long as it's non-empty and only positive formulas, you can decide on all of them at the same time. So this is kind of a way of doing multifocusing, if you will. And I don't know if you noticed before, but before, when the thetas in the and plus rule I gave, when the thetas were empty, this rule looked invertible. But now that I have multiple formulas in the focus, this rule finally looks non-invertible. So down arrow or the positive rules were the non-invertible inference rules. So now it's more clear why the and plus rule is not invertible. Okay, and now with these modifications, this is obviously sound and it's obviously complete. So there's no interesting theorem that I just stated about multifocusing. You have to check it's sound, but it's easy to see. And complete is true because every single focused system is a multi-focus system. The reason that you introduce multifocusing is it helps understand parallelism in a proof structure. And in fact, colleagues and I have written a couple papers where we take a parallel proof system like proof nets and expansion trees and show that maximal multifocusing, whatever that is, captures the same parallelism as these other paradigms do. And if I made a few of the changes, like I mentioned earlier, I can actually get the LKF to be a focused version of a mul, which is essentially already known by Andreoli back in '92, who is, of course, the guy who introduced this notation and the concept of focusing proof systems for linear logic in that case. Okay, so this is my conclusion. So I propose the LK system as an improvement on LK, especially for computer scientists interested in computational logic. If you're a philosopher or you're interested in algebraic connections between proof theory and proofs and algebra, maybe this isn't the right thing for you. But for the computer scientist, at least for many of us, I think this addresses many important issues. It's a flexible system. You can polarize many different ways. You don't have to commit to additive, connective, or multiplicative. They both work. And you can mimic many other proof systems, as I illustrated. And you can also, it also supports the inclusion of synthetic inference rules. And you can actually use it to prove things about unpolarized proofs, say, for example, Herbrand's theorem. And there is an intuitionistic version of LK, of LJ, and that's in an earlier paper by Chuck and myself. And if you need to know the references, I have them there. Like I say, the slides are available online, but I quit with this slide.